In example 2 from chapter 5, we have another first order system. This time the right hand side is made up of a step function, h of t multiplied by 4. In addition to that, there's a 3 times the h dot term for the step function, h of t. H dot is the unit impulse function here of delta of t. So what I'm going to do first is put this in standard form. That helps us compare our results here with what we found in lecture, which is true in general for first order. So I divide again by the coefficient appearing in front of y. So I get 1/2 y dot plus y is equal to 3/2 h dot, that's delta of t, plus 2 h of t as that. So this will be written as tau y dot plus y, and then I have a coefficient I'll call k1, define that in just a bit, another coefficient of k2 for h of t. Just a reminder here that the tau is equal to 1/2, k1 is 3/2, and k2 is 2. So what we're going to do is try to use what we learned for the general first order system to our inputs of the step and the delta and combine those. So when I take the Laplace transform of this, again using zero initial conditions because we're looking for forced response, I get tau s plus 1 times y. Right hand side I got k1 times the Laplace transform of delta, that's 1. k2, the Laplace transform of the step function, is 1 over s. So therefore our transform response y is equal to k1 divided by tau s plus 1 plus k2 s times tau s plus 1. So therefore, if I call this thing y1, looking at the different parts that are going into the transform response, I call this y2 and this y1. Inverse Laplace, I get that the forced response y of t is the inverse Laplace of excuse me, of y1. I'll call that y1 of t just to make sure we're clear on what this means. Transform response of y2, call that y2 of t. Well, from what we saw in lecture, this becomes the gain k1 divided by tau, e to the minus t divided by tau, plus k2, unit step function h of t, minus e to the minus t over tau. So again, what we have here is just a linear combination of what we had from our two examples of lecture of the step and the delta function. So k1 over tau, that's 3/2 divided by half, so that's a 3. And k2 is a 2 divided by the half. Oops, no, it's not. That's just the k2, isn't it? So this is k2, which is 2. The unit step, e minus t over tau, like that. And so since this is a 3, what I have here is a 3 minus the 2, so it just gives me an e minus t over tau. plus our twice the unit step function h of t. So how does this response look? Well, it's really made up of two parts. y1 of t and y2 of t. y1 looks like it starts out at 1 and decays down, so that's going to be something that looks like this. That's really some combination of our step and our delta function. So this is a 1. And then of course y2 of t is twice the unit step function, like that. So when we add those two parts together, it starts out at, when we add those two, it starts out here at 3. For a long time, it ends up at a 2. So it's a decaying exponential beginning at 3 and ending up at 2. So again, what we have here is when you have the right-hand side made up of two parts, the delta function and the step function, we can look at them individually, as we have in the lecture examples, combine those results in the end, and we get the total response, because this is a linear system, is a linear combination of those two parts.